Alright, in this video we are going to talk about K-map, the K-map, kernel map. Okay, which is a really powerful tool to simplify logic expressions and to simplify the logic circuits further. So K is a person's last name who developed this method. Right, kernel. Hopefully, I just pronounced it correctly. Right, and so this is used for being used to simplify logic expressions, or you can say logic functions, whatever you want to say, okay, which is just something describe the logic system the customer tells the engineer to do. And so let's try to get a K-map from the truth table and simplify from there and get a logic expression and get a circuit. How that works for the entire process, so you get a big picture about what it is. So we are using a truth table. I think it's a pretty old example we have been using for for last time. We can start having all these combinations of the input, just possibilities: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And the customer tell you when you have this kind of input, this type of input, you have to have 0 for this guy, 0 for this guy, 1 for this guy, 0 for this guy, 1, 1, 1, 1 for all the rest of them. Okay, and so whenever you see a truth table like that, usually the first thing you want to do is convert it into the K-map. So the way to do that is you put A here for the column and B and C here for the row. So for A you have 0 and 1 for two combinations. For BC you have 0, 0, 0, 1, and now be careful. So when you are listing all these combinations for BC, you only change one digit at the same time. So for example, after 0, 1, you cannot put a 1, 0 here, which means you're changing both this bit and this bit, which will not work, and I'm going to show you why later. So what you can only do is put a 1, 1 here and 1, 0 here. But just keep in mind in the future, it's not changing too much. You are doing the same thing, over and over again. It's the same stuff. And now we can find out. So from the truth table, what are these values? So you just fill in all these Y values into the K-map. So 0, 0, 0, you have 0, 0, 0, 1, you have 0, and 0, 1, 0, you have 1, 0, 1, 1, you have 0, 1, 0, 0, 1, 1, 0, 1, you have 1. So all the rest of them are 1s, okay? So now that's the K-map. That's it. So next, we need to group it. If you find out the 1s, you just group them together. They can be 4 1s, can be 2 1s, doesn't matter, but we have 4, so usually we just group all of them. And here we have 2 1s here, you group them. And now, when you are trying to write down all these, the logic term from this group, you are looking at A first. So see, this row has the same A, which is 1, right? So now you can start writing down the simplified logic expression. So this entire thing here have a 1 for A. So just write down A here. It's the same as a truth table. When you have A is 1, you just put an A here, right? And for all these BCs, you have all these 0s and 1s being toggled at every bit. every single bit. So that's why it covers all the cases, which means it doesn't matter for BC at all, actually. Whatever they are, as long as A is 1, you get a 1. Okay, let me say this again. So it doesn't matter for all these groups. So all these ones, what they are actually results for Y, and for all these things in this group, it doesn't matter whatever BC is. As long as you have an A to be 1, you are going to have a 1 as a result. So if I translate what I just said into a logic expression, it's going to be A, that's it, for the first term. For the second part, which is this group, and you can see that for A, it's A has been toggled, and so which means doesn't matter whatever A is, can be 0, can be 1, you are always getting a 1 here. However, BC matters, so you can see it's a BC naught, BC naught. So it's going to be BC naught. So you can get this result easily without bothering yourself by using all these theorems, like Boolean algebra theorems, and combine all these laws to simplify that from there. If you get a K-map, so this thing will do that job for you. So you'll get the same result. Okay. We'll show you more examples so you'll understand why we do that. So before we move forward, let me tell you two concepts that we missed from previous lectures. So the first one is MSB, LSB. So MSB means most significant bit. LSB means least significant bit. So when you have a binary number 11011, so the MSB is a bit here on the left side of the number, and LSB is a number on the right side. That's it. Okay, you just need to know this bit is called MSB, this bit is called LSB. They just have a special name. And another thing, for if you have Y, A, B, C, have a SOP here, which is a summation of all these things, M0, M2, M4, M6, for example, and all this little product, it can be A, B, not C or something, right? So whatever it is. So all this little product being combined by the AND gate, so it's called a minterm. And when you have a POS, so that's SOP, right? What about POS? Like this, right? And you have M0, M2, M4, M6. So every term here, for example, it can be something like A or B or C, and this one is called a max term. There's no technical stuff, just a name for these things, just a concept. Let you know, so when you are using that in the future, you know what are they, right? So next, more examples for K-map, so you can manage it. Examples. The first one, if I have this K-map 001, keep in mind, just change one bit. And I have something like that, right? So that's from a truth table. I didn't show the truth table, but this is what it is. And how can I group this kind of stuff? Definitely you can group in that way, right? But that's not the best way to do it. So usually if you see 4 ones appear here at the same time, just group them together. Just cancel all these things. Just group all the 4 terms at the same time. And now you can take a look. Actually, you can see that all the result, all the ones in this group occupied the 2 rows. So which means the A has been toggled in this group for the results. So which means A doesn't matter. Doesn't matter. If it's 0, it's going to be 1. It's 1, it's going to be 1 as well. So A is redundant. So only take a look at these 2. So for these 2, you can directly write down the result right now. B has been toggled 0, 1. So which means when B is 0 or when B is 1, it doesn't matter at all. They are always 1. So the only thing you need to write down is y equals to C. That's it. Okay, that's super simple one. All right, let's look at another example. If somebody just lets you know the SOP, for example, just give you this kind of form, M minterm 0, 1, 2, 4, 7. Can you get the logic expression and simplify that using a K-map? This is the only thing given to the problem. So when somebody write it in this form, this bit here is MSB. Here we go. That's why we introduced that previously. So that's LSB. Okay. So which means you know where these minterms locate in the truth table. So let's draw the K-map first. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay. So 0, the term 0, at that location you have a 1, right? What is that? So it's going to be 0, 0, 0. You have a 1 here. And 1, at location 1, you have a 1. 0, 0, 1, you have a 1. 2, you have a 1 as well. So 2 is 0, 1, 0, right? So 4 is 1, 0, 0. 7 is 1, 1, 1. So that's the K-map. And how can you group all these ones together? So you got 2 here, 2 here. Unfortunately, so 1, 1, 1 here. So you can do it in that way. Right, just cross the page. You can imagine that they're going to the 2 directions and being connected, on the other side. So it's open here, and this one doesn't have any place to simplify it. So no way. And now let's write down the logic expression. So for this one first, A has been toggled, so A doesn't matter, and B not C not is the first term. And now this one, C has been toggled, so C doesn't matter. You only have A naught and B naught. And this two here, B has been toggled, and you have C naught left, A naught, C naught. And that's a single one, you couldn't do anything for it. That's A, B, C. Okay, so that's the final result. One more example. So let's use Mike's term one. So for example, y a b c equals to this 0 to 4 7, for example, and so these terms are, we know they are zeros, right? So which means 0, 0, 0, you got a 0, and location 2, you got a 0, location 4, you get a 0, location 7, you got a 0. But all the rest of them are 1s. Okay, so now you can just group the 1s here and try to get the SOP out of it. So B has been toggled, A has been toggled. This one doesn't have any way to simplify it. Right, that's it. This is how you get a large expression, and then you can make a circuit out of it easily from this. And we will look at a little bit more complicated example here, which has 4 inputs. And let's see how that one can be simplified. Right. So right now the output has a name of F. A, B, C, D, which is, here's a minterm. I'm sorry, minterm. 0, 2, 3, 5, 7, 8, 10, 11, 14, 15. Right? And now we need to draw the K-map. 4 inputs, so we put AB here, CD here. You have 0, 0, 0, 1, 1. Keep in mind, only change 1 bit at one time. Same thing here. So 0 will be 4 zeros. You got 1 here. Location 2, location 3, location 5, location 7, location 8, location 10. 10 will be 1, 0, 1, 0. So 1, 0, 1, 0. 11, 1, 0, 1, 1. 14, 14 is 1, 8 plus 6, right? This 1, 1, 1, 0, which is here. And 15 is 1, 1, 1. So how can I group these things? All right. Oh, do we have an 8? So that's 8, right? So we must have something wrong somewhere else. Oh yeah, so that's 4. We don't have 4 here. Cancel that. And let's make sure if this is right. Right, looks right. So how can I group this? So definitely you probably already see this one as 4, 4, and 2, and then another thing which is not that easy to find out, but the 4 corners. Ooh. Don't forget that. Now it becomes easy. So F is equals to what? Now let's do it one by one. Not too many, just 4 groups, right? So let's do the corner first. So the corners, look at here. So the 4 corners occupies 2 rows, and these 2 rows has A toggle, so A doesn't matter. So you have B naught. For the 2 columns, you have C toggled, so D naught. That's for the 4 corners. That's this min term. And now look at these 2 guys. These 2 guys. Yeah, let's figure out the 4 groups. The 4 as a group first. So these 4. So all the AB doesn't matter at all because that occupies all the rows. And only CD. What about this one? B toggled, so A left. D toggled, so C left. Finally, these 2. Seems like nothing is being toggled on the row, so A not B will stay there. However, here C got toggled, so C doesn't matter, and you only have D left. So that's the final result for this logic, and that's it. So let's see if we have more examples for you. Yeah, so before we stop here, let me show you why you'll probably have a question. So why you want to just change 1 bit at one time when you list all of these things. Now let me show you one example. So why only change 1 bit for adjacent cells. Why is that? And now let's look at the example. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. That's the way we usually do it, right? So for example, you have this. These 3 locations has a 1 there. And usually if we do it, we're going to group these 2, and then we can get a logic expression out of it, right, after this. So that will be this. These 2, we have A naught and C. And these 2, we have A naught and B. Okay. Why is that? So why is this correct from the K-map? So the reason is, if we do not do the simplification by the way we just described over here, we just directly write down all these min terms as from the truth table. You know, just imagine this is not K-map, this is a truth table, right? So you can get something like just write down all the 3 terms over here. So what are they? So they are A naught, B naught, C, A naught, B, C, A naught, B, C naught. Okay, these 3 terms. And because we know something or something is still something, so let's just add this term again here. And now we can combine 2 of them. For example, A naught C, right? A naught C, A naught C. These 2 guys has a common term here. A naught C, and take that out. You have B naught or B. For here you have A naught B. So take that out. You have C naught or C. So 1, just cancel out that. And finally, you got A not C or A not B. Right, this is how that works. So when we are doing a simplification using a K-map, that is actually what is happening over there behind the scene. The reason is we just added a new term here, an extra term here. The reason we add it is because you can see that these two groups are reusing that term. So which is A naught BC, right? It's being reused. And now we can do it here, and then we can simplify easily manually, and that's what happened behind the scene when we are simplify everything from the K-map. And you can imagine that. So for example, if we do not put them in that way, but we change 2 bits at the same time, see how that will happen here. 0, 1, 0, 0, 0, 1. So logically, if we change 2 bits, it's going to be 1, 0, 1, 1, right? So now I still have 1, 1, 1, but the thing is, when you are trying to simplify, everything, you have to group them. So these two doesn't matter, you can group them, definitely. But however, for these two, you have to group, like that, in order to simplify that. If you are trying to, do the same, run the same thing behind the scene, but you have to group them in that way. So which is, not really convenient, and it's making things more complicated, but not helping. Okay, this is why we do in that way, and they have to change 1 bit at one time when you are going from left to right, and it's the same rules for 4-input digital system as well. All right, so that's everything for K-map you need to know, and I think you just need more practice from the homework, and you should be able to handle that in the exam in the future. Okay, welcome for watching, and I'm gonna see you in the next video.